Okay, so today we are going to be focused mainly on critical thinking and problem solving. So we're going to get a bunch of formulas today. So on this first one, we only have this one down at the bottom. Then we have this one at the top. And then we're going to get some things that go together. So when you go to do problems for this particular lesson, each one you get to, it's going to feel like we did not do one like this in class. There's no way that I'm going to be able to figure this out. But I promise that the things that we do today, you will be able to figure out with the notes that you have. So what we're moving on to now, and I think most of you feel okay about this. I don't know why it won't zoom in for you guys. Sorry, is it just slow? Like when I zoom in, this screen side doesn't zoom in for you guys at all. There we go. Okay, so I think you guys already have an intuitive understanding of conditional probability. So conditional probability is the probability that we assign to an event, or the idea that the probability of an event can change if we know that some other event occurred. So I highlighted that guy. I highlighted that your probability of an event can change if you know some other event occurred. Why do I keep saying occurred? So this goes back to the idea of flipping a coin. Coins have no memory, so those events are independent, and we are starting to talk about problems where they're not independent. One thing that you do will affect the next thing that happens. So how you typically see this is the probability of event B given event A happened. So this straight line here is supposed to represent the word given. So the probability that event B happens given event A has already happened. So that straight line is the word given. So we're going to explore this with a table on not traffic stops, but stop and frisk stops. So the table below displays data from New York City's stop and frisk program during the year 2011, obtained through a random sample of police stops. The program allowed police officers to stop people on the street and search them for weapons or contraband. The program was controversial because critics alleged that it led to a heightened police discrimination of people of color. So this table that you see is real data, real life data pulled from a government website that's listed here. So this is not made up data. The races that we're considering are Black, Hispanic, and white, and the force level is no force, hands used, or higher force level, which down here says that includes pushed to the wall or ground, handcuffed, draw or point a weapon, pepper spray, or they use their police baton. So no force used, hands used, higher force level used. So our first question says, well, actually, what I want to look at first is how many total stops did they sample? So I want to find, I think that we should just total up the race columns and then add them over. So I'm getting a total of 3,164 stops that we looked at. Is that what you guys get? Okay, so now I want to find the percent or the proportion of each race. So up here in this space, I want to find the percent of stops that included a black suspect. So P of B. I'm going to call black B, Hispanic H, white W. So the percent of black suspects is 1743 over 3164. So 55% of these stops involved a black suspect. That's a lot. So right there, we know that the majority of people that were stopped were of color. So I think that there's some credibility to this idea that this heightened police discrimination. Let's find the probability that they were Hispanic or the percent Hispanic. So 1113 for 3164. I'm getting about 35%. And then, as you probably suspect, I would like to do white suspects. %. So just by these percentages alone, without doing any conditional probabilities, it is obvious here that people of color were being stopped way more than white people. 80%, 90% of our stops would be considered people of color, I believe. So now we're going to get into conditional probability. The reason that it's called conditional probability is because we're looking at the event of something happening on the condition that another event already happened. So the first one is find the probability a randomly selected stop involved a higher force level given the suspect was black. So given the suspect was black. Okay, well, let's label these. I'm going to call no force N. I'm going to call hands used H. What do we want to call the higher force level?
Do we want to call multiple H's?
We can't. Uh-oh. No, we don't. Maybe we should call these A, B, C then.
We can't do B either.
Well, we can do... What? Well, we can do N. But what do we want to do for hands used? We could do HU, HF. So you can call it ABC if you would prefer, but I think I like those for me. So they're asking us P of higher force given B. So this is the probability that they're asking us to find. What's the probability that higher force was used given that the suspect that you are with is black? Well, that means when we go to find this, we have to adjust our denominator to only the black suspects. So in the bottom now, we do not use 3,164. We use 1743. So your given is going in the bottom. Your top then is the number of suspects that higher force was used on. So we're still in the B column. Higher force was used on 109. So we're finding the condition that higher force level was used. We're finding the probability that higher force level was used given you have a black suspect, or on the condition that your suspect was black. So 109 divided by 1743, so about 6%. I'm going to write it with 4 decimals. It doesn't matter what convention you use. You can do 0.06, you can write 6%, whatever you prefer. That doesn't seem too high. Okay, B, find the probability a randomly selected stop involved a higher force level given the suspect was Hispanic. So this time we're doing probability of HF given H. So we're looking only at the number of Hispanic suspects, so that's 1113 over 72 had higher force used. So this one is about the same, 0, 6, 4, 7. And then, of course, as you're probably suspecting, the last one that they want us to find is what's the probability higher force was used given the suspect was white. So this time, your bottom is only the white suspects, 308 over 18. So 584. So they're not asking us to answer this question, but looking at those percentages, it seems like black people are way more likely to get stopped than any other race. But once they're stopped, the force level is not really showing any discrimination. The white people is a little less, but they're all around 6%, 6.5%. So I would say people of color definitely getting stopped more, but once they're stopped, this, at least in 2011, so 10 years ago, the force level appears to be comparable or similar. Okay, last one. Given that no force was used, what is the probability that the suspect was white? So this time your given is at the beginning. So probability that the suspect is white given no force was used. So the condition this time is that no force was used. So I got to add up that row because the majority of stops were no force. I'm getting that 2,484 stops had no force. Is that what you guys have? And the number of white people that no force was used on is 260. So 260 divided by 2484, 1047. So there's a 10% chance that if you look at a stop where no force was used, if you look at a white suspect, there's a 10% chance that no force was used. Is that true? The probability that the suspect is white given no force was used. So if you look at the no force stops, there's a 10% chance your subject was white. That's what it's saying. Well, geez, that's pretty low. Okay, so down here at the very bottom is your generic formula for a given probability. And if you match that to what we have up here, you'll see that it's true. So what you do if it's A given B, notice that this given is what goes in the bottom always. You base your probability off of the condition that they give you. So if we wanted to compare that to what we see up here on this white given no force, what we really did find was the probability of white and no force, that shouldn't have a tail, over probability of no force. According to the table, that's the numbers that we pulled. White and no force is 260 in the table. This is the total number of no force stops, 2484. So every conditional probability, you can use this formula. Probability of A given B is the probability that both of them happen over the probability of the given or the condition. Okay, so this is how you calculate conditional probability. Now what they're going to add in is a tool that you can use to find the event A and B happening. Okay, brace yourself. Example 1. Your principal, Mr. McDaniel, has 8 red ties and 2 yellow ties. Each morning, he grabs a tie without looking, wears it, and then leaves it at school. Why is he leaving it at school? Maybe he's making some little kid wash them for him. I don't know. What is the probability he will wear a red tie the first 2 days of the week? Okay, so we're finding the probability of a red tie given a red tie. So this is, what's the probability that the first and second tie are a red tie? So it's the probability that the first is a red tie times the probability that the second is a red tie. So where does conditional probability come in? Well, they're telling me I got to multiply this stuff together. So they're telling me that this is the probability of R times the probability of R given R. So maybe this isn't right. What symbols would we use there? I don't want to write out all this first 2 days of the week. Let's call it M for Mr. McDaniel. I'm calling this event M now. So really we're finding the probability that Mr. McDaniel wears a red tie on the first 2 days. That's the event, M. Okay, please don't murder me. It's not M. I'm sorry. Don't be mad. Does anybody know what it's supposed to be, given this formula that I have ginormously written at the top of this paper? It's supposed to be R and R. What's the probability that the first is red and the second is red? Good golly, and I'm in charge. I'm sorry. Okay, so here I'm following this top part. The probability that the first is red and the second is red is equal to the probability that the first is red. So this means that the first is red. They get easier after this, I promise. Times the probability that the second is red, given that you already pulled out a red one. Okay, I feel better about this now. The probability that the first one is red is 8 out of 10. You have, or he has, 10 yellow ties in his drawer. The probability he'll pull out a red one is 8 out of 10. You're okay? Yes, no? Okay, this next part is what makes it conditional. What is the probability that the second is red given you already pulled a red one out? 7 out of 9. Don't worry, I don't always overcomplicate things. Okay, so 8 out of 10 times 7 out of 10.
9.
Yeah, I just plugged in my calculator wrong. $62. Is that what you guys got? There's a 62% chance he's going to wear a red tie on both days. That's pretty high, right? Okay, now that we got our symbols figured out, maybe this is going to get a little easier. Your assistant principal, Miss Tenbrink, loves mints and eats several throughout the day. She currently has 10 cinnamon, 5 spearmint, and 2 peppermints in her pocket. If she randomly selects each mint from her pocket, what is the probability that her first 4 mints will be cinnamon? Okay, this is the probability, and maybe you don't want to write this down, but I'm going to write it, of C and C and C and C. The first is cinnamon, the second is cinnamon, the third is cinnamon, the fourth is cinnamon. Well, we're basically going to do exactly what we just did. True story? Yes. So the probability that the first mint is cinnamon is 10 out of 17. Are you guys okay with that? What about the second mint? 9 out of 16. The third mint. The fourth mint. Then you multiply all that together. Yep, true story. What'd you guys get? 0.88?
0.088.
Oh, that's low. Less than a 10% chance? Okay, brace yourselves. This is right. I double checked it. You can trust me now. What we really found was this. The probability that the first is cinnamon times the second is cinnamon given the first was, times the third is cinnamon given the first 2 were, times the fourth is cinnamon given the first 3 were. But this is much easier to understand up top, right? So that's what you're going to focus on. You're not necessarily going to focus on this formula. You're going to focus on the idea of when you have a conditional probability, your chances change from one event to the next. Okay, next one. A poker player holds a straight flush when all 5 cards in the hand belong to the same suit and are in sequential order. Find the probability of a straight flush when the first card dealt is the 10 of diamonds. Remember that a deck contains 52 cards, 13 of each suit, and well shuffled, each card has an equally likely chance. Okay, so we want to know probability of a straight flush. I'm just going to call it straight flush. Okay. Well, they tell us that the first one is a 10 of diamonds. So we already know that that happened, right? So given that that happened, the next one needs to be a 9 of diamonds. So we already know that a 10 of diamonds has been dealt. So what is the probability we're going to get a 9 of diamonds? Well, how many cards in the deck are a diamond 9? 1. Out of how many cards left in the deck? This is already not looking good. Times the probability that the next one is an 8 of diamonds. 1 out of 50. Times the probability that the next one is a 7 of diamonds. Times the probability that the last one is a 6 of diamonds. 1 out of 48. That's going to be an extremely small situation. Ugh. Is it very small?
You put it in negative scientific notation, so yeah.
Great, I got you. I'm so good at that. It's like my favorite thing in the world. 7? Jeez. Okay, so basically this is what? Yeah, it's basically what value? 0. So really it's 0.6 zeros. 1, 2, 3, 4, 5, 6. We'll go 1, 7. So basically 0. And yet it happens because over the long run, there are poker hands that are a straight flush. That's when you go all in. You bet your $20,000 worth of chips. Yeah. I wouldn't go up. I wouldn't do that it's a... Because you would have to do, like... You could, but then you would have to do that it's a straight flush going down or a straight flush going up. So really, if that's what you were going to do, you just times this by 2. No, if you just did this, I think you'd be fine. Do you guys understand what Caden is saying? He's saying, well, don't we need to consider if the flush goes the other way? So it's a jack, queen, king, ace, 1, 2, or whatever. Jack, queen, king, ace. Well, yes, you could do that. So it would end up being that it goes down or it goes up. And to find that, you would just add these two together. Good question. You don't have one like that on the homework where it's unclear. Just to help out a little bit. We're okay on this one? Yes, no? Okay. In your dresser drawer, there are 6 blue socks and 10 gray socks, unpaired and mixed up. One dark morning, you will pull 2 socks from the drawer without replacement, because you need both. What is the probability that the 2 socks match? So this is exactly what Caden was asking about. So, probability of match, well, there's 2 ways that this can happen. you pull a blue and a blue. What's the other way? Or you pull a gray and a gray. Okay, well, the probability that you pull a blue will be 6 out of 10 for the first one. Then what for the second one? 5 out of 9.
It's 6 out of 16.
Yep. Yep. So 6 out of 15? 16? 5 out of 15? What do we do when we have an or? We add them. This is from your sample space lesson. When you're finding an or probability, you add. Probability that you pull a gray sock is 10 out of 16. Probability that you pull the second gray sock is 9 out of 15. True story? So what's that one? I wish the fraction wasn't such a pain in the butt on our big calculators. I'm getting 50% chance. That's pretty good. Okay, so beginning is conditional probability is that your probability changes given you know something already happened. You can solve problems with conditional probabilities like this. You have to remember as the events keep going, the probability changes. So this is the opposite of flipping a coin 4 times. Because flipping a coin 4 times would be a half, a half, a half, a half. And you would multiply them together. But this is not. You're okay on that? Was that a yes? Okay. Now we're moving on to the